Okay, another day, another stream. So today, um, I'm pretty sure I can keep this short. So let's get quickly started. Sorry, let's get started quickly. Um, so today, I just want to talk about shaders, um, but just a small note. I know I've not been able to put out videos as frequently as I've done in the past. I've just been caught up with some work stuff. Uh, So don't worry about the fact that the videos aren't coming. I will keep making them. Yeah. So today I just want to talk about shaders. Um, so in before we get and jump into shaders, let's just do a little bit of a recap. So we talked about GPU programming, and when we said GPU programming has two parts: the GPU and the CPU. The GPU is sort of a co-processor to the CPU. Um, so that's how you're supposed to think about it. The CPU is the one that issues commands to the GPU, and the GPU, processes those commands or works on those commands and then returns a response. Um, and the typical workflow is something that we went over when we looked at the high-level overview of what you'd call a GPU driver architecture, in a sense. So you have your application that you write, which uses something like a GPU API like Vulkan or Metal or DirectX. Metal is from Apple, DirectX is from Microsoft, OpenGL was the open source one. Now pretty much everyone's pushing for Vulkan. So that's the vendor runtime. That's what you'd refer to. And that's going to pretty much deal with the driver, the GPU driver, which is broken up into two parts, the user space component and the kernel space component. And then we've discussed the whole thing as to how you issue a command, how do you craft commands, and how do you send them through, and how do you synchronize, one, your commands, in the sense you want to draw something, but before you draw that, you want to ensure that you do, a couple of pre-processing steps and a couple of post-processing steps, and you want all of that synced up properly. So we talked about the entire pipeline of that, and how eventually, you end up uh, your commands end up getting processed by the GPU with something called a command processor, which is pretty much the brain of how to schedule work and all of that stuff. We sort of went through all that. So that's the host side of things. When we talked about uh, GPU programming and the GPU acting as a coprocessor, you're issuing commands, and those commands are making their way all the way to the GPU, and the GPU will be able to execute those commands. So that's great. So in fact, this is the harder problem, or not the harder problem. This is the what you'd call the more involved thing, getting this understanding the way the GPU programming APIs work and how you can access pretty much every bell and whistle in your GPU is something that takes a little while. And that's why you have these APIs, which is Vulkan, Metal, DirectX, etc. Um, the next step is, once you know this, what kind of work do you actually get the GPU to do? That's where shaders come in. So you've submitted commands, but what do those commands actually contain, in a sense? Um, well, there's some work that you want to get the GPU to do, and that work is what um, the way you express that workload is actually in what is called shader code. In a simple, in the simplest form of, if you want to simply talk about what shader code is, it's basically code that runs on your GPU. That's the actual instruction that will be executed on your GPU. And it's called shaders purely for historical reasons. It has nothing to do with, what we want to know, which is we want to do a lot of compute stuff. The reason it's shader code is because a GPU's origins is in the graphics world, 3D graphics, because a lot of 3D workloads are embarrassingly parallel, as they refer to. So that's why you called it a GPU. I think now it's time that we call it a parallel processing unit rather than, I don't know, a GPU, because it's being used for more things outside of just graphics. So with that said, now let's actually jump into uh, the core of what we want to talk about today, which is shaders. So as you've seen with the whole host side of things, there is some level of, you know, abstraction on the device side as well. When I refer to things as the device, I'm pretty much talking about the GPU. Um, Other accelerators also can be called the device in Vulkan's terminology. Just keep that in mind. So over here, we can have many different shading languages. Like you've written your, for example, this is your host side code. All of the stuff that we just wrote, everything that we just discussed so far, it's all host code. We haven't really given the GPU any kind of real workload. We've, except for this particular command, just as a example, you know, this is pretty much hitting the DMA engines in the GPU, but not really doing and not really invoking any of the GPU cores, as you would call it, right? But in order for you to actually do the work or get the GPU to do the work, you need to pretty much express that work, and that is usually expressed in these languages. Case in point, you might have noticed something. There is Rust can also be used as a shading language, and I'll tell you how that's possible today. That's a really I think that's where we're headed in the Rust space when we talk about GPU programming, and I'll get to that part. So MSL stands for Metal Shading Programming Language. That's from Apple, and Apple wants to do its own thing, and I'm not entirely sure why it won't play well with others. At least do your own thing, but try and play well with others. Anyway, so there's some problem with Metal in the sense that you can't transpile it directly to other shading languages. We'll talk about that. Then GLSL is basically the OpenGL shading language. HLSL is what Microsoft came out for its DirectX API. Slang is something that NVIDIA has open sourced recently. They've now made Kronos, which is the open foundation that actually manages Vulkan. They've taken ownership of Slang. That's why I've put it up there. And then WGSL is Web GPU shading language. So Web GPU is this other programming API that I had not talked about, but it is getting extremely popular. And you may end up, if you're not doing as if you're not as involved with GPU programming APIs as as your work requires you to be, uh, then you may easily get away with something like Web GPU because it's really good and there's a lot of momentum being built up on that front. So that's one. So these are all the shading languages. Now, what happens with these shading languages? Uh, the first thing that you need to know is shading languages are not as complicated as your general purpose programming languages, like say Rust, for example. So that means when we say we can use Rust, I'm not saying that you can actually use Rust in its totality. You can just shove it into a GPU program and then have the GPU running. GPU doesn't even have those instructions that general purpose Rust would need. So a subset of Rust is what is packaged into a shading language, and you can use that to go ahead and pretty much produce GPU specific machine instructions. The things that actually do that are these compilers, or rather, what I've listed over here are transpilers. So effectively, Naga is a pure Rust implementation of a transpiler. Previously, there was int, which is written in C++. It again does transpilation. And Slang is a language plus a compiler. So you'd be, so let me actually show you the Slang documentation. And that's kind of why I put it up there. apart from the Rust thing. Let me see. Okay, yeah. So Slang, uh, not Slang. We'll just read Slang. Um, right. Yeah. So this is the website. As you can see, the first thing I'd like to show you is, um, yeah, I put dark mode on, so something might get a little wonky. So let me just. Sorry about this. It's too bright. They don't have a dark mode. But in any case, you would see, was that? Yeah, it's now owned by the Kronos Group, which is basically an open foundation, and it's now under open governance. So that's good. So you don't have to worry about, some proprietary stuff that you end up learning, and you really can't move across boundaries, etc. So what I wanted to actually talk about was, yeah, what happens? How does this thing work? Let me see if I've got some documentation here. Mm, so I briefly went through this just so that they've got some good documentation and diagrams as well, so to make things easy. Um, hmm. Oops, it's like I'm looking at the wrong stuff. Um, right. Ah, yeah, that's what I wanted to see. Let's see their launch deck. Okay. Oh, this is great. You can go ahead and look at it. I just wanted to show you guys this part. So if you see this, this is exactly what a transpiler does. You can replace this with something like Naga, Tint, whatever. So you take a shading language as input, and then the output is another shading language or an intermediate format. So basically, it's doing source to source translations, or you can do source to an intermediate representation translation. And that's what these compilers do. Um, Again, as I said, uh, when we talk about GPU shading languages, they're not, as complex as a general purpose programming language. They're pretty simple because they're very, very focused, what you'd say, focused objective. They do a fixed number of things. That's what I want to say. And by virtue of that, they're not as complex as a general purpose programming language where you can express general purpose computations, right? Okay, so what we want to focus on, if we just go back, is we want to actually focus on, by the way, the intermediate formats are, you have things from DirectX will have its own intermediate format. That means it's using something called DXIL, and then MetalLib is something from Apple. Um, so these two are not exactly open source, they're proprietary. But here's the thing, I just saw this, which is, if you go to the SPIR-V website, you'd see that DirectX is adopting SPIR-V as the interchange format of the future. So it's very likely that, DirectX is not going to dump DXIL, but there's a lot more momentum that's building around SPIR-V. So, and it has the requisite, I can say, ingredients to actually be the one solution for the open source world. So that's the intermediate formats. So you can go from one shading language to another shading language using these transpilers, or if you go from one of these shading languages to one of these intermediate formats. All right. Now, not everything is as straightforward. For example, WGSL, as we call it, which is web GPU, is bijective in the sense that you can go from WGSL to SPIR-V and back to WGSL. So that's possible, but not with something like metal shading language. So when we talk about metal, it's usually you have written your GPU code in one shading language, but you want like output metal shaders because you want to ultimately work with an Apple GPU, then that's the workflow that you do. But the other way around, where you want to move from metal shading languages to others, I don't think anybody supported that because nobody sees a reason to support that, I guess. But yeah, anyway, so the idea is you go through this flow, and then once you're in one of your intermediate formats, then what generally happens, because we're only talking about Vulkan, is let's say you now have SPIR-V. You've written your GPU code in one of these languages, and then you've spit out SPIR-V. What happens is SPIR-V is not what you'd say uh, the machine-specific instructions for a given GPU. So each GPU will have its own instruction set, just like your own CPUs. x86, ARM, whatever, they have their own instruction sets. Like that, you have GPUs that have their own instruction sets. I'll show you what that looks like as well. Um, so you obviously need somebody to sort of do that translation, and that's not too difficult. That leads to the GPU vendors provide their own compilers that are sort of baked into the GPU driver that does all of this stuff, which is very similar to what I discussed when we talked about compilers like CraneLift. Not Pliron, but CraneLift, yes. We do instruction selection. CraneLift, we don't do scheduling. Register allocation, pipeline-specific tuning, all this stuff is what is done in the GPU driver with the help of the GPU-specific compiler that takes in input as one of these intermediate formats and produces vendor-specific GPU code or GPU machine code. And then the last piece that I also want to talk about is now that you have this machine code, you theoretically you'd like to, sort of when you're developing stuff, you want to know whether everything is working correctly. So you want assemblers, disassemblers, shader validators, and you want to be able to optimize things if you can, that is. So there's tools for that, shader RC, SPIR-V tools, etc. All great. Um, there are Rust versions for this. I think it's called RSPIR-V, which wraps around SPIR-V tools. I haven't checked it out, but yes, that is there. So effectively, this is the flow. You write your code in a shading language, depending on which particular workflow you'd like to go with. Let's say we go with Vulkan, and I'm working with Mac. So I probably let's say I write my shader code as well in Rust or in WGSL or in Slang. I take the stuff, I put it through something like Naga, and Naga spits out MSL. That's what I take and give it to the GPU driver. And this is not something that I would do. This is what the Vulkan API would do, finally, because we're not exactly talking to a Vulkan driver per se. We are talking to what you call an Apple driver. So ultimately, you will need to give it a metal shader, and that would go ahead and Apple's driver would go ahead and do all of these things and produce Apple AGX instructions. And there's a very nice blog post where I believe the SI folks have reverse engineered Apple AGX instructions. I forget who did that. And yeah, who? Yep. Yeah, this is the one. So you can go ahead and look at this. It's going to take you a while if you want to like stare at the machine instructions. But so that community, the open source community on the Linux side, not particularly Linux side, but the graphics team that deals with Linux, they've gone ahead and reverse engineered this and made upstream the driver, etc. So you can still see the instructions, but it's not uh, it's not an ideal flow that you want to deal with. Anyway, so that's a typical flow. And when we talk about generic shader programming workflow, this is kind of what you're talking about. And the reason I'm calling this out very clearly is because I want to compare and contrast that with the new languages that you keep uh, hearing about if you're working in the compute space. which is things like Triton from OpenAI, PyTorch, and TensorFlow have their own ways of directly accessing GPUs, etc. How do they work? We'll talk about how do they work, including the new language called Mojo. We'll also I haven't really written any GPU code in Mojo because I don't know how to, but it follows a similar principle. I want to contrast that with this. All right, this is your generic, like this is the regular workflow. You take CUDA, sort of goes through this, doesn't need all of this stuff because it's one single flow. Nobody understands CUDA except NVIDIA's tools and stuff, but a similar workflow. And the rest of the GPU programming APIs use this flow in some manner or form. All right. So the one thing I wanted to say is in Vulkan, when you do something like you want to create a graphics pipeline or a compute pipeline, that's when the Vulkan driver takes your SPIR-V and converts that to native machine instructions. So there is some amount of a runtime cost involved, right? Note that this is not render time, and that's kind of what Vulkan helps you with. So in the OpenGL world, this was not the case. You used to do these GPU or shader compilation during render time as well. I haven't worked with an OpenGL. So if anybody knows better, correct me. But I presume that will be the case. But at least in Vulkan, you force applications to compile your pipelines and your shaders, etc., ahead of time, so that you have more predictable performance. You don't do unexpected shader compilation at render time, right? So that's a key point that I want to call out. And to top it off, you can probably do this statically as well. That means you could go ahead and do this part, that is this intermediate representation to machine instructions part ahead of time. Because ultimately all you do is the GPU driver is going to give it to the vendor specific compiler. So why not just do that ahead of time? So that's possible. And that's what vendor tools provide, like NVIDIA, AMD actually have a way to do this. And you can produce your compiled machine code for your specific GPU and then bundle that. You don't have to do that extra step. And the other thing that you can also do with Vulkan is you can do caching, which is once it's compiled, you don't need to keep recompiling this if you've enabled VK pipeline cache and stuff like that. All right, so that's great. And so why is SPIR-V the interchange format of the future, right? So if you were to look at that, by the way, I'm switching over from Firefox because of what the hell happened. I have no clue why they went from we're all about privacy to we don't give a rat's ass about privacy. I have no clue. I do like Firefox though, but maybe we'll figure it out. But what I'm hearing is, they can sell data to anyone, is what I understand. Anyway, I'm not happy with that. Cool. All right, that's that's a detour. So I was talking about SPIR-V as the interchange format. In this case, this is why Vulkan and Vulkan's ecosystem is something that you should probably bet on, is because there's a confluence. There's a lot of uh, folks wanting to get involved in this ecosystem because of the vibrancy of it, as you can see. You have all these guys like TensorFlow, PyTorch, the graphics guys, the compute guys, the general legacy compute is what I'd call them. They're all in here. They're all targeting SPIR-V in some form or manner, right? And then you've got SPIR-V cross, which does the cross compilation, or transpilation. And all of these pieces are sort of already being worked upon in this Vulkan ecosystem with SPIR-V. So it's got a good future, is how I would put it. All right. And there's a lot of resources for you to get started. The spec is very clearly laid out. There's stuff like the registry that contains published Chronos vendor extensions, etc. There's a SPIR-V guide, the tools part that I mentioned that does a lot of processing, developer time, stuff like you need an assembler, a disassembler, all that stuff, right? And there's also an LLVM tool. This is one thing that I want to talk about. The LLVM SPIR-V translator. It's not part of the LLVM. Uh, it's not, part of the official branch, I guess. But it's something that will help you. If you have LLVM IR, you can convert that to SPIR-V, or you can go back to LLVM IR. So that's something that's already out there. Great. So this is why I say that SPIR-V is the interchange format for the future. It's got a real good community backing. It's got great, at least, documentation that's becoming better and better by the day. And there's a lot of people, including a lot of the big players, supporting it. So the future is good for that. And with many players trying to adopt it more aggressively, I think we're going to see more and more usage in many different places. Right. And then the other point I wanted to cover, the shaded dev tools and transpilers. I think we already sort of covered this. But even before that, let me actually show you something that is uh, very interesting, because I wanted to get to the part where I, like I've talked about all these shading languages, but not really showing you what they look like. I don't have time to I haven't really gone through a full working example of how you'd put one together in Vulkan and then make everything work, because I'm working on that part. Just need a little more time on that. So let me just I hope this has dark mode. This is perfectly fine. You can see this. So this is a very nice interactive web tool. You can put it that way, where you can basically go ahead and type your own shader code in these languages. Rust is included in here, and then that will produce the corresponding, what you'd call shader code. And in this case, if you see this over here, this is DXIL, I guess, right? This is produced by from this is the DXIL, equivalent of what is on the left. And the way that happens is the guy that made this is Tim Jones. Is pretty, pretty, pretty useful one. This is wherein the actual DXE compiler is now available. It'll just take it up. It'll go ahead and produce this format. Yeah, and don't try to add a compiler. I know that it keeps failing. For example, let's say I want to take something like, let me take Rust, right? Yeah, this thing takes a while, just so that you know, because obviously it's not supported by some big player, etc. It's one guy who put all of this together for the community. So I presume this will be the case. But anyway, you would now see that Rust would be sort of converted to SPIR-V, right? Because it's kind of what we're aiming for. Right now, the Rust workflow, or Rust as a shading language, only works with SPIR-V, right? So here's what you get. This is what SPIR-V looks like. Don't worry about all the stuff, which is op capability, everything else. Everything in SPIR-V is an opcode. That's what this is trying to tell you. But we'll get to this part, not today, but we'll get to it. And you'll be able to see a couple of things over here. For example, if I chose, I don't know, let me say if I chose Wixel, which is the most popular shading language right now, just because it targets the web. So as you can see over here, you will have a huge number of compilers that support it. Naga, Tint, even Slang, I guess should support it. Or maybe not Slang. So again, when you use Naga, you'd be able to support it to all these different formats. So if I had a Wixel Cedar code, this is the code that's actually going to run on your device. This would be, I could actually produce SPIR-V, I could produce Metal, I could produce HLSL, or GLSL. It doesn't make sense to produce WGSL from it, but fine. So that's sort of what's going on over here. If you remember correctly, I did go through another another, what you'd say, another stream of mine where I talked about um, kubectl. It's another one of these things. It's the same thing, right? Um, it does transpilation as well. There, you write your Rust code, you annotate it properly, and then it is able to produce all these other shading languages. Case in point, let me show you how this thing, the WGSL code, can be converted to something like Metal, right? So I'm going to use Naga itself and produce that. Should take a while, but yeah, this is what your Metal shading language looks like. It's some version of C++. I believe it's C++14. Yeah, it's got templates and stuff, which is what makes me cry. But uh, anyway, so this is what uh, shading languages look like and what SPIR-V actually looks like. You already saw what SPIR-V looks like. Maybe let's bring that back. Sorry. Oh, sorry. So it'll come up. So that's what SPIR-V looks like. I'll just leave it over there. So that should give you an idea for what this entire pipeline is going to look like when we do write the shader code and we go about working on it or working with shaders via Vulkan. The thing that I'm still trying to figure out is which one of these languages should I use? There are three things that I'm very interested in. One is the Rust. We have Rust GPU. The other one is Slang, which is actually very full featured. And you know what? It actually looks like Rust. And I'll show you what that means. And then the third one is WGSL, which is the most popular one at this point. But there are limitations with each. So Rust is going to help you because you don't have the cognitive load of learning two different languages and trying to figure out stuff. You can just learn one. But the problem with Rust is it's not, what do you say, mature enough. It's a project that works. There are uses of it today in some projects, like some gaming projects apparently use Rust in, I think, a limited form. So the reason this, what do you say, Rust to SPIR-V works is because of this project called Rust GPU, I believe. Where is that? Okay, sorry, wrong word. Right. So Rust GPU is the future of GPU programming, as the team is putting it. So there's uh, the original guys that actually worked on this was a game studio called Embark. Now it was taken over by some folks from the Rust open source community and said, we want to keep, you want to steward this in the right form, give it a lot of attention because the other folks weren't able to. So we now have Rust GPU. Okay. So I really want to use that, but uh, it's also important to go look at something like Slang because just look at the feature. There's millions of lines of Slang. It's already been written because this was actually funded by NVIDIA in the initial days. It was apparently called GL Slang. It has things like interfaces, which are traits. It has things like generics, which Rust has. So it feels very much Rust-like, as you can see over here. So that's good. It also has things like auto differentiation, which is a first-class citizen. So it helps with things like mural rendering, which is the hotness right now. Because I'm not interested in that, but I'm interested in the auto differentiation part. Also, it's got really good integration with something like Python, etc. So it's fully featured, it's well supported, and all that stuff. Ideally, you want to go with this, but then what happens when you go down the line? That's the question, right? Uh, all right, so that's where we are. As I said, I don't want to take up too much time. I just want to keep this little piece in mind. The one last thing I want to talk about when we talk about shading languages is just so that you're not sort of left out. Let me see if I can find my previous project. So I wrote what you would call uh, a tiled matrix multiplication, or that uses shared memory, uh, which is the programmable cache in the GPU, um, to sort of talk about how you naively implement matrix multiplication, then go to the the faster ones till you sort of hit the fastest possible implementation that you can hit. So there's a very nice article that I would highly recommend, which is that, yeah, by, I can't pronounce his name. I think his name is what? Simon? I'll just call him Simon, right? So I hope he doesn't take offense, but yeah, at least it's SIBOM is what he is. And so this guy goes from this naive, writing a naive CUDA kernel, and then going all the way till it's, you know, competitive when compared to something like CUDA's own library called QBLAS, right? So you sort of do go through all these little steps and get to that part. How do you do that is the question. So I just wanted to show you at least the part that I did, which is this, but I had to do it in metal, which was a headache because I didn't know any C++. Anyway, so let me try and see if I can find that for you. Where is that? Mm, nope, it's not here. Ah, probably on. Hmm. Where did I put that? I'm pretty sure I put it in Rust. You know what? Let me just show you here. What am I not even on for? So yeah, so you can go look at this crate. I'll leave links in the description. Um, where I've basically done some very, very basic experiments. So there's a matrix multiplication experiment where there's two types of metal shading kernels I've written. So this is how you write uh, metal kernels. Um, this particular kernel, there's two parts to it. One is the tiled version, as you can see here. You just increase the font size there. So the tiled version, and then the simple map null version, which is the naive version. Both of them are available. So you'd be able to see a couple of things like how we load a chunk of your matrix into shared memory, and then do the do the matrix math on that chunked versions, and then accumulate that into a result, and then keep doing that, and you'd be able to really see a speed up because I've done the measurements as well, and you'd be able to see that somewhere here, maybe. No, readme. Yep. Yeah. So you'd be able to see that over here. We have like some serious speed ups if you go through the math. So yeah, I just wanted to sort of give you a flavor for what shader programming is all about. Uh, and very specifically, when I talk about it, usually when you go and look at some of these compute kernels, as they call them, you'd see that, okay, all this host code is missing. What am I talking about? All this Vulkan metal, this stuff about? I don't see any of that in, let's say, something like PyTorch or TensorFlow, etc. The reason for that is because that's actually abstracted out. You don't deal with the runtime at all. You don't deal with the GPU source code at all. You pretty much express your ideas in whatever language they've offered you, and then that's going to go ahead and produce um, the relevant GPU instructions. For example, in Python, as you can say, sorry, in Mojo, there is no explicit host API that I'm aware of. All this stuff is actually handled by the Mojo runtime for you. you're not doing this. And right now, the only runtime, GPU runtime, or they're targeting at this point, I believe, is NVIDIA. They have ideas for the other ones as well. Not, uh, it's not yet ready, is what I understand. So that's Mojo. So it's all about what would that really look like? And the best example I have is from something like Triton. So this looks like Python. When you write a kernel, a compute kernel in Triton, and this is what it looks like Pythonic code. And that's exactly what Mojo looks like as well, I presume. However, if I'm wrong, please let me know. And then what happens is this stuff is going to go through a compiler pipeline. Primarily, it's going to go through something like MLIR, which I've discussed in detail in other videos, especially my Pleron video, where I'm talking about the Rust equivalent of MLIR. So you sort of get this, and then from here, where did that go? You sort of go through this entire pipeline. Let me just make this a little bigger. So you go from here, you get MLIR, you push that into LLVMIR, and then you translate that to SPIR-V. And then, you know, you go from SPIR-V to whichever machine instructions you want to go to, right? So that's sort of what you'd be seeing right now when we talk about. That's the difference when we talk about your regular generic shader programming versus your compute focused one. And if you wanted to see you want to do the same thing, which is you want to do something like what Mojo does or what Triton does or what PyTorch does for compute world, you want to see how that's done on the graphics world. There's this cool little website called Shadertoy, I believe, which everybody loves. So you can go here. There's a lot of people building a lot of stuff. And you can just browse around. You'll be able to clearly see, people building different kinds of shaders. And the way to build a shader is, I don't know, just click this, and you'd be accept. Yeah, I accepted that, and you'd be able to see the entire shader code right here, right? So this is another similar form. You are not writing any of the host code. You simply go ahead and work. So when you don't actually have to work with the host code, you're limited. Just you need to know that, especially in this shader programming world. You're not doing intense 3D graphics, etc. over here. You just want to make some really good artwork, or you want to do some what's that called? Uh, there's a whole field that works on this. It's called artistic programming. I don't know. I don't remember the word, but yeah. So you can build a lot of cool websites as well with this stuff. So this is what you can do on the graphics side, and this is what you can do on the via MLIR usually, what you can do on the compute side. But in both scenarios, you have to keep in mind that you don't really deal with the host code, right? That's automatically done. So yeah, that's what I wanted to sort of show you, or rather talk about today. And that's pretty much what I will be focusing on for the next few videos, is picking one of these languages and then sort of doing what um, this guy, what Siboin did for CUDA. Let's see if we can do this for Vulkan, right? Just go through these pieces, see how you can make your simple thing, your matrix multiplication. But let me just sort of do this. How fast you can make your matrix multiplication, but using Vulkan and not something like CUDA. But since I'm using a Mac, I'll have to go through Metal and stuff. I'll see how that works out. God knows. But anyway, so that's shading languages, or a lot. That's shaders at this point. Great. Any questions? You can please feel free to go ahead and drop a comment. Thank you for all those folks who've been really, engaging and posting your questions and thoughts and all of that. It's been really helpful. The whole reason I do this is because I want to learn, and so that's it. Okay. Thank you. Have a good day.